Hello, welcome to today's Coreform Cubit Learn webinar. We'll get started in just a few seconds. Hi, welcome to today's webinar on Coreform Cubit Learn, a critical part of an efficient, free student FEA software pipeline. I'm Matt Cederberg. I'm the Coreform CEO, and I'm joined today by Greg Vernon, who will be presenting today's webinar. The webinar will be recorded, and please feel free to ask questions to us throughout the webinar using the questions and answers. So today, the agenda that we'll follow, this will be probably about a half hour. We will first introduce you to Coreform Cubit, then we'll give an overview of just the simulation workflow process, talk about how to build a free software stack, which we think will be of particular interest to students and academics, and then demonstrate how Coreform Cubit can be a part of that simulation workflow. So we hope that you'll learn by the end of the webinar is to better understand the engineering simulation process, to have greater awareness of powerful free and open source research tools that can be used for the entire FEA or CFD pipeline, and then learn how Coreform Cubit can be a critical part of that workflow. So first of all, just to introduce Coreform Cubit, if you're not familiar with it, this software has been used for several decades for advanced meshing for challenging simulations. It has a broad suite of tools. It has CAD import and cleanup tools, so it natively imports STEP, but you can also get translators to import directly from popular CAD programs like CATIA or NX or SolidWorks. Probably the sweet spot of where Cubit's used most often is for semi-automated hex meshing. There's a lot of controls to get maximum mesh quality. And then also Cubit's used heavily through the Python scripting interfaces. So Greg will be showing some of that in the workflows today. Coreform Cubit Learn, we released this a year or two ago. It's a free license of Coreform Cubit that provides all of the access to these tools to hobbyists, students, researchers, and others. And the only functional limitation is that you can only export up to 50,000 elements. But besides that, you have full access to the full suite of Cubit tools that Greg will be showing you today. If you are an academic and you need unfettered export access, we have heavily discounted academic licenses as well. So you can just reach out to us if you start to use Cubit Learn and then you need a larger element size export. So with that, let me just ask a quick poll before I turn the time over to Greg. So we're just curious why you're attending today's webinar, so we can understand a little bit more of the background and tune this to you. Curious if you want to understand how to build a free academic simulation workflow, if you're using other simulation software, perhaps free software or other commercial software and you're looking for something a little bit more powerful, or if you already are using Coreform Cubit and just want to know how to use it better. So let's leave this open for another couple of seconds and share the results out with you. Okay, so here's the results. It looks like the majority are looking to understand how to build a free academic simulation workflow, which is perfect because that's going to be most of the focus today.
Does this show up if can people actually see the poll results, or do I need to? Am I sharing it now on my screen?
Oh,
for folks?
I think I'm sharing it, so they should be able to see it. Yeah, and for those that are already using Coreform Cubit, we will reserve some time at the end for Greg to really ask Greg anything if there's any outstanding Coreform Cubit questions that you've got. So with that, let me introduce Greg. So Greg Vernon is the Director of Engineering at Coreform. He used Cubit professionally for 8 years prior to joining Coreform, and so knows the software quite well. And this webinar was actually motivated by some presentations that Greg has given to students in academic settings where they've been looking exactly to do exactly this, to set up a free stack to do academic research and simulations. So with that, let me turn the time over to Greg.
Thanks, Matt. Yeah, as Matt said, this did kind of come around that I just finished off my graduate school, and while I was in graduate school, I was helping various students who were doing their own research and were needing meshing solutions, and had talked to some professors who were also looking for, what are the different solvers that are out there and kind of strategies and things that that they might be able to use to solve both kind of physics research problems and engineering research problems. And so I had put some stuff together and some thoughts together, and that's where this kind of came from. So, so with that, we'll just dive in. The first thing I want to just kind of introduce is just like the general simulation workflow. So there's kind of like 4 key areas that if you're building your workflows that you should be considering. And the first 2 steps are kind of sometimes where a lot of manual labor can go into, but it's model preparation and then mesh generation. Oftentimes those 2 things are pretty closely combined, but we'll show just maybe what the differences between those 2 things are. All or large portions of those can actually be done completely within Coreform Cubit. And then you've actually got the simulation that actually runs, and then you're doing your post-processing, your analysis of your result. So at a high level, that's kind of what goes on. Obviously, you can do like iteration loops with this for like optimization, which I'll also talk about later. So to start off with with workflow for model prep. So there's a couple things that you're oftentimes going to be doing is, you've got some new novel material. You're trying to figure out what kinds of maybe plastic or plasticity model works well for it. Maybe you're trying to understand, it's a polymer, and I want to understand like the bulk properties of it during compression. Want to understand maybe cycles until it kind of gets to like a steady state for like an aging. So there's like a Mullins effect that occurs. So you'll have some test data typically, and then you'll want to be trying to fit this test data to different material models to run some analysis. And so you're calibrating your material model. And that's just even before you're even able to maybe look at your engineering scale problem. There's also kind of model parameter development that you'll likely be doing. So you maybe for instance, like on a melt pool for like laser welding or for additive manufacturing, you might be doing like some small breakouts just to try to calibrate maybe like what are the laser parameters I need in order to get a weld pool that looks like what I'm seeing experimentally. Again, before maybe I can calibrate a lower order model for like my actual engineering problem. So I kind of like throw these together. That oftentimes these do end up using simulation, especially when you're trying to then validate that your model is correct. But you might just be grabbing like a phenomenological model and then just trying to fit parameters to those, and use different tools for that. So that's like a lot of data analysis that you might be doing there. Another kind of part of that model preparation is kind of like what I kind of call geometry prep. I like to segregate this from like the physics that's going on to a certain extent to like now say I've got geometry, and maybe if I'm doing a forging of this axisymmetric part, I could run the full 3D model, and I might want to run full 3D at some point, but I can do a lot more iterations if I idealize it to an axisymmetric model. And I can run maybe thousands or tens of thousands of axisymmetric models to get maybe a couple candidates, and then I can go back out to like quarter symmetry or full symmetry to then flesh out the fine details between my candidates. So idealizing the problem can oftentimes take millions of degrees of freedom down to a few thousand degrees of freedom. And then also defeaturing. Part of defeaturing is just so that you can even build a mesh on a geometry, but also that there's oftentimes especially in large assemblies, there are regions you just don't care about. You might have seen, hey, I got a fatigue fracture that occurred in this fillet in this specific part of the body, and I just want to understand, the plastic strain increment in that fillet. And so I don't need to waste degrees of freedom and waste computational expense on other parts of my geometry. So I'm just going to defeature those so I get general forces so that I can trust in getting accurate results in my fillet, which I won't defeature. So I kind of call this is kind of like where the practicality of simulation really comes in at. And then I mentioned that we have mesh generation as the next step. And this is really just taking whatever your CAD geometry is, and you've got to put a mesh on it so we can discretize it, so we can solve our partial differential equations on it. Even if it's just a simple elasticity, it's still a differential equation that we need to have a discretized model. And again, there's a whole bunch of strategies that we'll go into for maybe you want to do TEP meshing, hex meshing, or a mixture thereof. Maybe you want to do like shell elements. So you want to have a meshing tool that can then build for you the required discretizations. And then lastly, so workflow is kind of like the simulation and the post-processing. Oftentimes you'll just like iterate here. So this is just a couple examples of having like a physical result. You're trying to validate your computer model to it. You want to have tools that allow you to maybe investigate or interrogate your results to see if they match what you're seeing physically. This is a picture of results from peer review. But also, a lot of engineering actually gets done on probe data. So it's like these simple XY plots on the right here. And that's where a lot of analysis is done. A lot of times you'll do like the visualization to kind of get general feels for what things are happening and make sure that things look correct. But then especially as you're actually doing engineering work and you're optimizing, you put a probe and a fillet, and now I'm just going to track, over as I change the radius on this fillet, what's the stress value do? And what radius do I get underneath maybe a certain stress value that I need to have? So being able to do both plotting of 3D graphics as well as plotting and analysis of kind of time history data is valuable. So there's kind of those like high level just explanation of what those different steps are. I want to talk about then when I've talked to researchers and graduate students about building kind of their software stack, how I kind of recommended they do that. My first recommendation is to choose your solver. And I tell them to start by asking what's the primary functionality or use case that I need from this solver. And it kind of comes down to two large categories. You've kind of got like the standard functionality where I just want to solve an engineering problem. Maybe I work on the Formula One design team at the school, and I've got a bar that has bent, and I just want to understand like what the loads are and maybe what I can change about this bar to not bend in the future. Maybe you're a researcher in biomechanics, and I just want to be able to do some analysis on an ACL ligament. Excuse me, just a second here. Stifle a sneeze. So in those kinds of cases, you might be looking at tools that I've kind of listed down here that are really focused on application end use. Yes, they can be extended, but their purpose is to be extended by kind of maybe a core team, and it's really the motivations for end users to get engineering applications done. So in there, we've included things like OpenFOAM, which I'm sure folks have heard of, as well as Calculix and FE Bio. And then the other one is, I want to develop maybe a new novel method. Maybe got new ideas for quadrature or to how to handle locking of elements. Maybe for my problem, I actually need to solve a novel PDE or a novel coupling of PDEs. And so I really need extensible frameworks. And in those cases, then I suggest folks look at kind of this other variety of code, such as like Moose, FreeFM, DL2. I will say that some of those codes themselves also have kind of standard functionality for applications. For instance, Moose has a has already modules that have been developed by Idaho National Laboratories for tensor mechanics, as well as like thermal analysis. And so if they've already happen to have some of that functionality, it makes it a lot easier to like just add a little bit on top if you need to, unexpectedly later. Oftentimes you'll find out what solver you need based on um, other academics in your field and what your community is using. But I kind of recommend actually having one code for each, because sometimes even though you're doing focused R&D, sometimes I just have problems that come up where I just need to just solve the problem and solve it quick. And so I oftentimes would run with both, or a tool that provide both functionalities. The second step is then to identify your model prep tools. And these are kind of, again, what do I need to do in order to like, be able to fit or calibrate material models? What do I need to be able to do to analyze experimental data? Maybe I need to store data. So kind of all the common players here. While MATLAB's not free, oftentimes you have it available at your academic institutions. There's also the new Octave, which is a open source version of it. But then Python, Julia, again, Excel or Sheets or some other spreadsheeting application, as well as Dakota. I point out Dakota because Qubit does have a native Python API. It does pair well with Dakota's Python-based, what they call a black box interface. Now, Dakota is an optimization framework, but also like automation. So if you want to run a design and experiments, you can use Dakota to set up and communicate with through Python to Coreform Cubit, and then whatever your solver tools are, what the parameters are that you want to be doing for a current study. You can set it to automatically execute maybe off to your HPC system, or run locally. I actually did my my graduate thesis using Dakota, and it's a great open source tool for that. So so if automation or optimization is something that you're looking for, I highly recommend looking at Dakota. Step 3 is to choose your meshing software. Obviously, this is a Coreform Cubit webinar, so I'm going to highlight, or I'm going to highly suggest to use Coreform Cubit, but there are other tools that are out there. And especially if you're working in very focused fields, where maybe your entire work is done on microstructures. It's there's a microstruct Python module that is focused for building meshes for microstructures. And so while Qubit has like a general purpose functionality, if you are working in very focused application fields, there oftentimes are meshing tools that are very well focused. There's actually even, I didn't have it on here, but there's even meshing software specifically focused for like external aerodynamics of an airplane or of an aircraft. And so if you're doing external aerodynamics of a 787, I would recommend going off and grabbing those tools that are laser focused on that application area. There's also other professional tools as well. So I'll talk maybe about why some of the features about why you might want to choose Coreform Cubit coming up in a little bit. But I just wanted to be open out there that you need to be able to choose what meshing software is going to work best for you. The fourth step is I recommend folks to choose a visualization tool. And this really is, in my opinion, for 99% of folks, this is peer review. It's really a best in class general purpose visualization tool that has both the 3D graphic visualization as well as XY plotting access. There are certain of those solvers that we mentioned previously. There's a solver called MFEM that has a purpose-built post-processor called GLViz. And then there's also certain applications that there's an open source, or at least a freely available code called Visit from Lawrence Livermore National Laboratories. And you kind of know if you need to use Visit. So for 99% of folks who are out there, you can just pick PeerView and feel good with your choice to use PeerView as your visualization tool. You can obviously also write your own bespoke visualization tools in, say, Python with Matplotlib or MATLAB or something like that. Then I recommend choosing a file format. And why a file format lasts? my opinion is that if you look at the tools like Qubit and ParaView, as well as the solvers, they oftentimes allow for a variety of different input files to be used. I do recommend that you try to gravitate towards the input file that has the most native support in the solver you're picking. And largely there'll be some combination of, or some selection of these, but there's also some text-based input files. I know that a lot of open source tools have built upon the Abacus input format or off of like ANSYS format. So you can certainly use those as well. I want to point these out that what's nice with these tools is like DTK is natively supported by ParaView. There's also this Exodus file format, which is natively supported by Qubit. It's actually the file format that Qubit was developed around originally. And what's nice about it is it's actually part of a larger project called CCAF. So I'm going to open up a web page here to show to folks, which comes from Sandia National Laboratories, actually an acronym. And it's essentially a suite of tools that allow engineers who are using government simulation tools that maybe Sandia or Lawrence Livermore or Los Alamos provide to access that data. And so it includes that Exodus file format. And what's nice with Exodus is that there is a Python interface for Exodus. So again, all through Python, you can actually go in and query results or even create from scratch an Exodus file. You can go in and grab variables from the Exodus file just through Python if you wish. There are also tools that if you chose to use something like MATLAB as your analysis tools, there are converters, Mat to Exo and Exo to Mat, that convert to and from Exodus and MATLAB. There's also tools for doing domain decomposition of Exodus files, so split them off into multiple parts to rejoin parallel decompositions back together. It can be converted to a text-based format to and from. So there's a lot of functionality that's really helpful from an end user perspective if you go the Exodus route. In addition to it being the natively supported by Qubit. I think every graduate student who does work in finite elements takes a class where you have to write a finite element code from scratch. And I actually wrote my personal grad finite element code using the Exodus format. And so I was actually able to use Qubit to write out Exodus and then load it into my Python-based finite element code. So I personally highly recommend the Exodus file format. But again, that's a decision that you need to kind of weigh all the different options together. So I want to just give like an example then. This is an example that I helped a researcher at Brigham Young University put together. So again, we looked at what are the capabilities that they needed to have. They needed to have a mixture of being able to extend where they needed to. They needed to be able to add maybe some simple PDEs to their model, but they also needed to solve some very standard thermomechanical problems. And they wanted to be able to run in parallel. So we chose the Moose finite element library for them as having kind of the best of both worlds of everything that they needed. They, on their end, they kind of already had some of the model prep tools, right? They're already using Excel. They're already using Python. Knew they wanted to use Python more. They weren't aware of Dakota. They'd written their own kind of scripts in Python to try to automate their workflows. We could show them Dakota and how they could use Dakota to automate a lot of the work that they had been doing. We then suggested to them to use Qubit for obvious reasons. And that worked out really well for them. But again, that fit that pipeline of being able to go from model prep through to simulation. And then they used ParaView as well as some Python for doing some fast Fourier transform analyses as well. And then once we kind of built all this together, we got a whole bunch of different exporters out of Qubit that we could choose for meshes. moves can take a couple different input formats. So we chose Exodus then as kind of like the tool or as the mesh format that we're going to be using to pass data, through all of these different tools. So it's just like a real world example of how we built a mostly, in this case, they were using the Qubit Learn, so it's a fully free pipeline for them. And then if they want to extend on to do larger models, then they can. So I just wanted to then show some of the features of Coreform Cubit in a simulation workflow that maybe make Coreform Cubit a really good option. So the first here is a really critical part of doing analysis is, you have to define the geometry of your simulation. This is an example of an old IGES file from a repository that came in, it's all shells. I need to be able to heal this geometry into a solid volume that I can then run analysis on. I got these cylinders that are on a solid region, and then this cavity that's going to be a fluid region. And so I was able to, in Qubit, do all the fixing I needed to do to turn those from shells and sheets and maybe some sliver surfaces into a solid body that I could mesh and run analysis on. So I haven't even done the meshing yet for that. But then once I've got that solid body, then I can stay in the exact same tool and then actually build the mesh. And this is, Qubit provides the ability to build meshes from 0D up to 3D. So if you're doing like paradynamics or SPH or RKPM, so particle-based methods, discrete element method, you can actually even mesh these zero-dimensional sphere elements all the way up to, in this case, this is a mesh that has a mixture of tets, pyramids, and hexes. So there's a pyramid interface between the hexes and tets in this case, so it's a fully conforming mesh. But all the tools, such as being able to decompose your geometry in order to build the hexes, are provided by Qubit. And we alluded to this earlier. There's a bunch of tutorials and previous webinars. If you're interested to learn more about how hex meshing works in Qubit, that you can go off and look there. Qubit also allows you to assign sets to put model parameters onto. It allows both the idea of assigning sets to geometric entities, and then whatever mesh elements are then owned by those mesh or CAD entities, then inherit maybe a set assignment. So, whoops, let me see here. In this example here, I've got some side set, so I'm going to apply maybe some inlet and outlet conditions and some displacement boundary conditions on these geometric surfaces. And then once I build the mesh, all the quads and triangles that are parts of those surfaces will then contain that information. But also then that Python API allows you to both extend the existing functionality in Qubit to do what you want it to do, as well as be able to use it externally. So the first example here, I'll just show it on the left here, is what I wanted to do is I wanted to be able to set a mesh size, but what I needed to do is I needed to set it per volume. I needed to set a specific size, but I always wanted to have the smallest element sizes or the smallest volumes control the element size. So what I needed to do is I needed to find the volume of every single CAD volume, and then I needed to sort them and then loop from largest volume to smallest volume and assign a mesh size. And so it'll do that very simply then in Qubit Python. Another option is, say that you're using an external tool. In this case, we're going to use FireDrake, which is a Python-based finite element library similar to Phoenix, if you've used that. So I'm going to have some external Python that's provided by FireDrake. Is actually going to then import the Qubit Python API and initialize the Qubit server. But then everything is, I can run, get further down in this static image, we can't see, but I've got my entire FireDrake simulation profile. It actually calls off this build geometry, which then runs Qubit, fills in parameters, is able to build the mesh. So suddenly now this simulation in FireDrake, you can just run Python, this script, and it'll automatically run your analysis for the full workflow. So it's a really unique ability to be able to use the Python functionality both in your CAD GUI or inside their GUI, and as well as in a separate applications Python that can, as long as it's able to import that. So those are the key functions I wanted to show. We're gonna have a little bit of time afterwards. I think Matt alluded to that if folks would like to see some demos of things, maybe using Cubit to build some meshes, maybe a quick walkthrough through some of the Python application areas, I'm happy to do that as well. But again, you can find all of our past webinars on YouTube, on our YouTube channel. So I think with that, Matt, I think we have a final poll for folks.
Yeah. So we'll just, when you eventually leave the webinar, we will have a survey for you where we'll just be asking you what solver you're using. If you'd like to answer, it's actually an anonymous poll. They'll just help us as we identify which solvers we can develop additional training material for. So that might be helpful for us. But yeah, beyond that, we just have some time for any questions and answers, any at all, whether about the material Greg presented on. A number of you had said that you are currently using Cubit. You are looking to see how you can use it better. So if you'd like Greg to do any demos of anything that's been vexing for you, we can stay on the line for a minute and answer any questions.
Yeah, I guess there was one question. I think it did get answered, but just to say it verbally. So if you are using the Cubit Learn license, which again you can sign up for, maybe I'll show where you can sign up for that on our website. If you are running into this 50,000 element export limit, if you need to get around that export limit, you can just email sales@coreform.com. And we can then get you sorted out and find a solution that works for you. To find Cubit Learn, so let me pull up coreform.com here. So if you go to our homepage, under the drop down under Coreform Cubit, there is a link for the free edition. And then through here, you can register then to get Coreform Cubit Learn. So that's where you'd go if you wanted to get that. And again, if you then, this should send you an email from Coreform Sales. So if you'd like to then extend beyond the 50,000 export limit for commercial or academic use, you can just contact us through this.
All right, let's see. Got another question. I am facing some display issues with Cubit on my Windows PC. Who can I contact for support? So there's a couple of ways to get support for Cubit. Greg, since you got the website pulled up,
Yeah.
maybe you can just pull up the form.
Yep.
So we are very active on our website form. So this is probably the best first place to come with any questions, because then anyone else that may have the question in the future can benefit from the answer, and others besides us can chime in with support. You're also welcome to email just support@coreform.com as well if you have confidential or specific questions.
Yep. Yeah. Okay, there's also a question. Someone's curious to see a very simple example with a finite element solver and post-processing. Planning to use Cubit in a graduate course at their university. I'm curious to understand how they can start with students. So like an elastic beam element with loading. So yeah, so I can give a quick example. So I'm going to give a quick example here using Moose. So I'm going to use, one of the reasons why I like to use Moose as well is that, so I have Windows 11. I also have the Windows subsystem Linux loaded up on my Windows machine. So I can, without having to dual boot, I can access Linux. And you can find information about If you just Google Moose Find Element, it should bring you to the Moose framework page. And then like under getting started, they have a good example of how to install Moose, and even for Windows with Windows 11. So they still call it experimental, but I've had really good success with this. So they give you different steps to do. What's nice is also with Windows 11 that you can now access the Linux data just through your Windows Explorer. So you can actually have tools like PairView. You don't have to worry about moving files around. You can literally explore your Linux partition. So I do recommend, that's an option you can look at as well. But then for that, what I've done is, so I've got the Moose repository that I've cloned. And there's a process in there where what you do is the Moose repository is just where the code is, and you build applications on top of Moose. So they have a script that's called Stork, where you can create your own application. So I've actually done that. I've created an application called struct mech, and it has like a make file. So in this case, I just want to use existing functionality in Moose. And so I've kind of said, okay, of all the different modules that Moose developers have already added, what module do I want to build? So I said, I want to build tensor mechanics, which is where their solid mechanics functionality is built into. And so I said, build that, the simple, make, you just literally type make in here and it goes and it compiles. I like to then kind of carry around a little problems directory inside of my applications. So I've got I think I did a demo on this. I might have done a demo on this earlier last year. But just through following some of the different examples inside of the Moose repository, I put together an input file for my problem. Again, I'm using the Exodus mesh, so I've told it that I'm going to use a mesh that comes from an external generator. So this is my geometry Exodus file, which again I built using Qubit. And then to run this, see if I've got this in my history here. Yep, so I can run even in parallel, so maybe like 8 cores of just a simple MPI execution. And I just need a Mamba activate Moose. And so now the Moose solver is just going to go through and run my problem for me. So from a development standpoint, I had to change just one thing in the make file and type make in a terminal. And you do have to kind of have some ability to navigate a terminal application to be able to use Moose. It kind of goes for most of the open source applications. But what's nice is I've already loaded up the results from that file. So I just loaded up the Exodus file that it spit out into PairView, and then I can do my different visualizations. So I can look at von Mises stress on elements. I created a user variable in that Moose input file for max principal stress. So I highly recommend Moose. I think it's great from a graduate student perspective, where you just want to get up and going and start solving problems, and then know that you can also extend it later. So that might be where I might recommend you start looking at.
Great. Thanks, Greg. Okay, another question. I want to mesh a turbine blade where the geometry is very curved. Should I use Coreform Cubit or Coreform IGA? One thing that I realized we didn't mention about Qubit is that we do have support for smooth spline U-spline elements. So maybe we should just allude a little bit how that can be accessed in Coreform Qubit.
Yeah, and I'll say also, if that is something you're interested in, are the smooth U-splines, we do have some initial functionality we've been working with INL or Idaho National Laboratories on with Moose to be able to run with U-spline elements in Moose. Your mileage may vary just because it's in the early stages of that, but sure, I can show inside of Qubit. if we have a geometry. So I'm just going to create maybe a sphere, radius 1. I think my graphic tolerance here, I'm just going to crank down a little bit. The default. So there's a mesh scheme inside of Cubit for sphere. So since it's a sphere, we're going to go ahead and mesh with the sphere. Maybe we're going to do a coarser mesh here. Here we go. So a nice coarse mesh of our sphere. Obviously, this is from a linear element perspective, it's pretty coarse. If you want to then build a U-spline, we can do things like set the U-spline parameters. We'll just do quick and easy here. We'll build U-spline on volume 1. And then we'll just fit the U-spline. So the build built the basis, and now we're actually going to fit that basis essentially to our geometry. And we can then visualize that U-spline here on the right panel. So if exploring U-splines is something you're interested in doing, or exploring high order smooth splines, we're also developing a kind of a modernized version of Bezier extraction file formats. That's if you work with spline basis functions, that should mean something for you. But that might be something that you might be interested in talking to us about.
Yeah. Yeah, so I just suggest, just chiming in on the forum, and we'd be happy to engage you with any questions about IGA. Then another question for a tutorial, I guess more of a tutorial recommendation. Workflows for dealing with complex geometries would be greatly appreciated. I have a geometry being hashed with the auto hex meshing functionality, and areas with curvature have many relevant quality issues. Talking about different common errors and reasonable solutions would help. It sounds like, Greg, that may be the sculpt command that he's using. But in any case, maybe you could pull up, we've done a few webinars, both focused on sculpt and on just tips and tricks for meshing. Maybe you could pull up on the webpage just so we could kind of point some of those out.
Yeah.
And
under
if you just go to webinars, it's under support, the webinars.
Oh, okay.
Yeah, so some of the ones that may be helpful here, the September 2022, semi-automatic hex meshing of complex parts is a good one. May 2022 is showing how to use sculpt. But if you have these complex geometries, feel free to, again, the nice thing about working in the academic space is often these are non-confidential, and if you are able to post them on our forum, then that's a way that we can help. And if it looks particularly interesting, we could even use that as a subject for a new webinar.
I will say one thing that can oftentimes fix a lot of issues with Cubit, and this has come up in recent days on a separate FEA forum that I was helping out with, is that there is an idea of absolute tolerance in CAD. So at the base of CAD, there's what's called a kernel. So whether you're using SolidWorks, CATIA, NX, they all have a kernel at the base. And to my knowledge, every kernel uses an absolute tolerance due to some issues that come up with doing Boolean operations on complex surfaces. And so that absolute tolerance, typically you'll find a maximum absolute tolerance or tightest tolerance of like 1E minus 6. And a lot of tools actually use a lighter tolerance by default, and you have to request that. So Cubit uses that 1E minus 6 absolute tolerance as a default. So oftentimes when you import a geometry, like say if I import like this blade geometry, something I recommend doing is, what you kind of want to do is look at your geometry and kind of decide what's the smallest feature I actually care about keeping. And so in this case, maybe what I'm going to care about keeping is, I'd say, like these fillet curves are like the smallest feature I care about, that I want resolved in my mesh. Because oftentimes what will happen is through CAD software will sometimes do a vertex viz on here. It's gonna kind of like mock this up. What'll happen sometimes is that CAD software might say put a might create like a small little surface. So I'm just going to do this like on this curve. This curve, I'll just create 2 different vertices. I'll split this surface. Oops. Put this surface through these 2 vertices. I probably didn't like that. Let's do plane from curve. About this, clicking around here. $61. Okay, so like say that there's like a very, so pretend that these are all as one volume, but what will happen a lot of times is it just through CAD operations, you'll get like this really thin sliver curve. They'll just show up. And that's just, you're gonna want to defeature that away. So we don't actually want to keep that. So what I recommend doing is, again, find the volumes that you care, the sizes that you care about, and then scale your model so that the length of that curve is around order 1. So you can see here that curve length, if you look at our properties page, is like 3, which is around order 1. So we don't need to worry about scaling this geometry, but say that we did, say that import this same geometry. Say that it came in and it was scaled way far away. So if I just scale this model by 1 minus 3. So you might have brought this model in. You find the curve you care about. You find that its length is around 0.003. So again, what that means is that as I do partitioning of my geometry for hex meshing, that I've already used up several orders of magnitude of my absolute tolerance that I have available to me. And so even if, this might be units of meters, so maybe it's like a 3 millimeter long part, what I would recommend doing is scale this model, by a nearest power of 10 to get you up to around order 3. So I'd scale up by 1,000, do all my meshing workflow there to get myself ample tolerance for Cubit to work with, and then scale my model on export. So it's something that Cubit kind of makes it available to you as like a user able to actually work with that absolute tolerance. So it kind of exposes it. So it's just like a one trick that I see that a lot of times with highly curved geometries that they'll have like some small curves or small surfaces that are really close to the absolute tolerance. And so the scaling is kind of something that needs to be done. So anyways, kind of went a little bit deep on that, but just thought that's one big trick that I would recommend if you're having some issues. It's to look at the scale of your model.
Great. Thank you, Greg. I really appreciate it. And thanks everyone for staying on this webinar. We hope it's been informative to you. And you can stay in touch on our forum and let us know if you have any other questions or ways that we can help. Again, if you wouldn't mind answering the exit questions so we can know what solver you're currently using so we can prepare more material to support you, we'd appreciate it. And hope you have a wonderful rest of your day.
Thanks.